So in this video, I want to talk about if you have a vector, such as the one I've drawn already, that is in magnitude and direction form. You can see that's the case here because the vector I've drawn, it has a length 10 meters per second, and it has an angle 50 degrees counterclockwise from the positive x-axis. If you have a vector written in that fashion, how do you determine the components of that vector? Okay, so first thing, by the way, I decided for this one, you'll notice the magnitude of the vector is 10 meters per second, which is not really a length. One point I wanted to make is when we say that the magnitude is the length of the vector, sometimes we mean that quite abstractly, because remember, vectors could represent actual physical distances, but they can also represent velocities or accelerations or many other things. So sometimes the magnitude of the vector isn't literally a length. Sometimes it's just an amount, a size, a whatever you want to call that. Amount, I guess, is the best word, of how big, how strong that vector is. So in this case, it's a 10 meter per second vector at a 50-degree angle. Okay, so let's call this vector, we'll call it vector v because it's a velocity vector. I can see from the units that it's a velocity vector. Okay, so if we have that vector, the question I want to answer is, what are the x and y component of that vector? If we know the magnitude and direction, what are the x and y component? So how do you do this? All right, so step one. Step one, put in an x and y coordinate system. Draw in your x and y axes. I'm just going to use the standard x and y axes all the time. So let me draw in my y-axis here. So the x-axis is already there. So this is the positive y direction, and this is the positive x direction. Okay. Step two, I want to turn this vector into a right triangle. I want to turn the vector into a right triangle. So I'm going to draw a line parallel to the y-axis and a line parallel to the x-axis to complete the right triangle. So let me drop a line down like this, and the other line is going to overlap with the axis like that. And let me write this down too, because I want to make sure you know the steps of how to do this. So draw a right triangle whose legs are parallel to x and y axes. Okay. Once you've done that, the leg parallel to x is the x component of the vector, and the leg parallel to y is the y component. Let me try to organize this a little bit better, actually. And the hypotenuse of the vector is the magnitude of the vector. Okay. So now I've turned the vector into a right triangle. That's the really key concept. You can turn a vector into a right triangle. Once you've turned the vector into the right triangle, I mean, look what I have here. Let me just redraw it for emphasis here. I have a right triangle that looks like this. I have 10 meters per second on the hypotenuse. I have 50 degrees here. I have the x component of the vector down here. Usually we denote the x component with, since this is vector v, v subscript x, and the y component will be v subscript y. Okay, so you'll notice that this is just a right triangle with two parts of the right triangle specified, the other two parts not specified. How do you solve a triangle like this? And the answer is use trig, use trigonometry. If you're rusty on trigonometry, I made another video in the intro module to review how you do this. But step 2 is going to be use trig to solve the right triangle. So in this case, we would want to use sine and cosine to solve it. We would have sine of theta is opposite over hypotenuse. I have a 50-degree angle here. So the side opposite of the 50-degree angle is going to be Vy because it's on the other side of the triangle from the 50-degree angle. So opposite is going to be Vy, which is unknown, and the hypotenuse is going to be 10. So this means that Vy equals 10 meters per second, if I multiply that by both sides of the equation, times sine of 50. 10 meters per second times sine of 50. And if I compute that, sine of 50 times 10, I get 7.6. Or 7.7 actually, meters per second. And then likewise, I can do the same thing for the cosine for the x direction. So cosine of 50 is adjacent over hypotenuse. The one that's adjacent to the 50-degree angle is Vx. You can see there because it's touching the 50-degree angle, and the hypotenuse is still going to be 10. So this means Vx is 10 meters per second times cosine of 50. And that gives me 6.4 I got. And if you want to do a little double check here, we also know Pythagorean theorem holds for this. So if we do here 6.4 squared plus 7.7 squared, and then square root that, we do in fact get 10 as the answer, as expected, because that's the magnitude of the vector. That's the hypotenuse of the vector. So these two, this is the y component of the vector. This is the x component of the vector. So one perfectly good way to specify this vector would be to say the vector v is the vector which has Vy equal to 7.7 meters per second, and Vx is equal to 6.4 meters per second. And that's just as good a way to specify the vector as saying that it's 10 meters per second, 50 degrees counterclockwise from the positive x-axis. So those are two equally good ways to specify the vector. You'll notice that they both contain two pieces of information, not just one. Other thing I should mention here, it didn't come up in this problem, but components of vectors, unlike the magnitude, they can be positive or negative. In this case, both of them were positive because the vector's up and right. So the point at the end of the vector here has a positive x coordinate and a positive y coordinate, but the components could be positive or negative. So you might have to add in some negative signs. I'll show you another example where that comes up, but you might have to put some negative signs in front of the components as well. Most important thing here, most important takeaway is just draw the stupid triangle. It's really, irritating actually that a lot of people who take this class, when I teach this lesson, they're like, I don't need to draw the triangle. I'll be fine. And then they just keep making mistake after mistake after mistake, converting these things over. Please don't hesitate to draw the triangle. Draw the triangle and you'll get it right every single time. If you try to solve this without drawing the triangle, you might get it, but there's just so many possible little mistakes you can make that you definitely, whenever you convert between a vector, and magnitude and direction and components, make sure you draw the right triangle and then solve the right triangle. And if you do that, it'll be easy.